Hi, so in this video we are going to discuss a very important skill, and it's to recognize common structural patterns which generally have resonance structures. Okay, so there are really 5 such patterns which you should really try to recognize, and it takes a lot of practice. These patterns, if you recognize these patterns, it will help you predict really when resonance occurs. And so what are these patterns? First of all, we have allylic lone pairs, and I'll explain what allylic lone pairs are in a second. Then we'll have allylic carbocations. We have lone pairs, or a lone pair which is adjacent to a carbocation, a pi bond, which is between 2 atoms with different electronegativities, and finally we have conjugated pi bonds in a ring, all conjugated pi bonds in a ring, in an aromatic ring. So you see allylic, the word allylic appears over and over again, so I have one slide on explaining what allylic means. Essentially, allyl just means that an allyl atom is an atom right next door to a carbon-carbon double bond. So, for instance, if you have this structure where you have a carbon-carbon double bond in the middle, you will have 4 allylic positions here highlighted in green. You see these positions are right next to the carbon-carbon double bond. And so we look for allylic lone pairs, so carbons or other atoms which are right in an allylic position, which have lone pairs there, because these lone pairs generally are resonance stabilized. To give you an example, there's a structure. Question is, which lone pairs in the structure are allylic? And then we have 2 nitrogens. And so the nitrogen which is next door, which has a lone pair and is next door to the double bond, that's the allylic one. The one up here, the one on top, is not allylic because there's another CH2 group in between the nitrogen and the double bond. Alright, so we've learned what allylic means, and now we're going to talk a little bit more about pattern number 1, which is exactly the allylic lone pair. So I'm going to draw a couple of examples for you guys, and they will be all allylic lone pairs, and I'll draw the resonance arrows to show you how to go from one resonance structure to the other. I'm not going to draw all the resonance structures so that you can do yourself. So in general, we need 2 curved arrows to show delocalization of an allylic lone pair. Okay, start with example 1. This is called an allyl anion. It's allyl anion. And you see I have a lone pair which is allylic, a carbon with an allylic lone pair next to the double bond. To delocalize it, to draw the other resonance structures, we draw the following. We draw these 2 red arrows. Okay, here's another example. Now we have an oxygen with an allylic lone pair. It can be delocalized again in the same fashion to the double bond, into the double bond. Here we have an ester functional group. Right, you can again delocalize the lone pair, the allylic lone pair on the oxygen. And okay, here goes with a carbon atom with a lone pair again, an allylic carbon atom. Here now we don't have a carbon-carbon double bond, but we have a carbon-nitrogen double bond. You can do the exact same thing. And finally here we have an amide with a carbon-oxygen double bond and an allylic lone pair on a nitrogen. Again, we can do the same delocalization pattern. Okay, so you have to keep track of formal charges when actually drawing out the resonance structures which result from these arrow pushings, which we have just drawn. You have to be very careful. So when the atom with the allylic lone pair initially has a negative charge, then the negative charge, after you push the arrows to get the other resonance structure, the negative charge will be delocalized together with the lone pair. Okay, so in the allyl anion, this is the allyl anion, we push the electrons like we said, and we draw a resonance arrow, and now we're going to draw the other resonance structure. It looks like this. But you see now we moved the anion, the negative charge, from the right carbon to the left carbon. So we have to draw now a formal charge on the leftmost carbon of the structure, right? And never forget to put the whole thing in parentheses. So brackets. Okay. Now, if the allylic atom is neutral, it will become positive, and the atom receiving the lone pair will become negative. This we can see in an amide, right? So here the nitrogen, which has the lone pair, is neutral initially. We push in the electrons towards to the carbon-oxygen double bond, and so the structure we get now has a negative formal charge on the oxygen and a positive formal charge on the nitrogen. So practice this, and a good way to get started is with conceptual checkpoint 2.18. Alright, second pattern would be similar to allylic lone pairs. We now have something called allylic carbocations. So that's just a carbocation which is next to a double bond. And in this case, we only need one curved arrow. And so here's how it works. This is allyl cation, which we have already seen. And this is the curved arrow, which gives us the other resonance structure. There we go. Okay, again, you see the positive charge has moved from the left to the right in the structure. And so if there are multiple double bonds, you can extend this pattern, then many more resonance structures are possible, of course. So how do you draw these other resonance structures? You just move one electron pair at a time. And we'll draw an example. So this is a more delocalized carbocation. It is delocalized over 5 carbon atoms. Right? These 5 carbon atoms are all sp2 hybridized, and so now we can start moving one double bond, and we get a new resonance structure. Then we can move another double bond, we get another resonance structure, right? And so again, put the whole thing in brackets to show that these are all resonance structures. Now practice this, please, with conceptual checkpoint 2.19. The pattern number 3 now is a lone pair which is adjacent to a carbocation. So here again we only need one arrow, and I drew already an example structure. We can draw the arrow to push the lone pair to the carbocation to make a double bond, and we get, in this case, acetone. Okay, so that's a relatively straightforward pattern. We can do the same thing with the next structure here, and in this case now the oxygen gets a positive formal charge. So what you see whenever you draw resonance structures, this is very important, the overall charge of the structure is always the same. Right? In the example above, we started with we had a neutral structure, and initially we had the two charges, the plus minus on the top left structure, were balanced, so it was neutral overall, and then in the other resonance structure on the right for acetone, it's also neutral. And in the second structure, we start off with a carbocation, so it has a +1 charge, and it keeps the +1 charge. Right? In the other resonance structure, it's just the +1 charge. Where the charge is located is moving. It's either on the carbon or it's either on the oxygen. So, yeah, recognize how the formal charges are affected here, and keep practicing this pattern, this resonance pattern, with conceptual checkpoint 2.20. 2 more patterns to go. So pattern number 4 is pretty much the reverse of what we just discussed. So they're actually the same pattern. The book wants you to learn it in both different ways, forward and backwards, so it's easier to recognize for you in practice. And here what we basically have is a double bond, a pi bond between atoms of different electronegativity. So essentially what happens here is the pi bond, if the two atoms have different electronegativity, the pi bond will be polarized, which means the more electronegative atom gets more electrons. And so we can show this with resonance structures. Again, we're basically doing what we did before in the opposite direction. So here's a double bond, carbon-oxygen double bond. You know oxygen is more electronegative than carbon, for sure. Right? So it wants to pull the electrons toward itself. And so this is how you draw this this electron pulling towards the oxygen, and it gives us another resonance structure, which again we saw before, and we have to draw in the formal charges. Right? So now essentially what we drew, these two structures represent the extreme situations, right, which are never really true. So in one case of the structure on the left, the electrons are fully shared between the two atoms, so there's no charge on the carbon or the oxygen. In the right structure, it's the electrons are all pulled towards the oxygen, and so they're not shared at all. Right? So in reality, it's a structure in between. It's again a hybrid, as we've always said. That's what resonance structures mean, and there the electrons are essentially unequally shared. So you get a delta plus on the carbon and a delta minus on the oxygen. Right? Again, this concept you should keep practicing with checkpoints, conceptual checkpoints 2.21 and 2.22 and 2.23. Okay, the last pattern, which you're going to see quite often, the last resonance pattern, is conjugated double bonds in a ring. So many double bonds in a ring. Essentially, in this situation, each atom in the ring is sp2 hybridized and has an empty p orbital, which can then overlap with all of its neighbors. So this can, the most common example is benzene. It's called benzene. It's an aromatic ring, the simplest aromatic ring, and it has 3 double bonds, 6-membered ring. So now you can take all the double bonds and move them around all at once, and you get another resonance structure, which is equally valid as the first one. So in reality, the electrons again are shared. You basically have half a double bond between all the carbons, and yeah, you can. In this case, you can actually push the electrons either clockwise or counterclockwise. So I've done it in a counterclockwise fashion, but it doesn't matter how you push the electrons. You get the same structure out, and so it doesn't matter. You can push it either way. Both ways are correct, clockwise and counterclockwise. Yes, please practice this type of resonance pattern with checkpoint 2.24. So I just have a summary slide on all the patterns we discussed. So we had allylic lone pairs where you need 2 curved arrows, again, and pay attention to formal charges which are moving around. Then we had 1 curved arrow for the allylic carbocation case, and we had 1 curved arrow for lone pairs adjacent to carbocation. Then we had a pi bond with between 2 atoms of differing electronegativity, which is essentially the reverse of the pattern before. And in the end, we had the rings, which have all sp2 hybridized carbon atoms, aromatic rings. Okay, so please keep practicing with conceptual checkpoint 2.25 and all the problems referred in there. Thank you for watching.